Welcome. In this video, the goal is to demonstrate the use of the different methods of calculating work done for the same problem. So the sample problem I'm going to use is problem 24 of chapter 8. I believe this is chapter 8 or maybe chapter 7. But the point is we're going to calculate work, and in this situation we have a book that's being pulled by a horizontal force. So a horizontal force is acting on it such that the book slides up a ramp. And the ramp is frictionless, and we told the mass of the book is 3 kilograms. And there's a force that's applying on the book. The size of the force is 20 newtons. And the angle of inclination for the ramp is 30 degrees. The amount of displacement the book will undergo is half a meter. So what I have done, just to keep the video brief, is I have over here highlighted the forces that are going to be acting on this. So the first part of the problem is that they asked us, and that's the only part I'm going to do, they asked us to find the net work on the book by the different forces. So by the force applied, so by this force, and also by the force of gravity, so that force, and by the normal force. So these are the forces that are acting on the book. So we need to calculate the work done by them. So remember how work done is calculated. When the force acting on an object is constant, work done by that force is going to be equal to this thing here. The dot product between the displacement vector together with the force vector. But remember that this is also actually equivalent to the magnitude of the displacement vector times the magnitude of the force times cosine of alpha, where alpha is the angle between the force in question and the displacement the object undergoes. So let's consider, when we are interested in the work done by the normal force, right now I'm going to demonstrate, let's start off with this approach. In other words, we're going to use this part of the dot product. So what do we need here? We're going to need the magnitude of the normal force. We're going to need the magnitude of the displacement vector and the angle between the two. So notice here they are attached tail to tail. And what is the angle between them here? It's going to be 90, because the displacement is up the ramp and the normal force is perpendicular to the ramp. So what we can say is that the work done by the normal force in this situation is going to be the magnitude of the normal force times the magnitude of the displacement vector times cosine of 90, and we know that this is going to be 0 joules. Okay, what about the work done by the force of gravity? Well, notice that when they're attached tail to tail, the angle between the displacement vector and the gravitational force is actually given by this. This is the angle. The dotted line here, which is nothing more than the extension of the normal force, is perpendicular to the displacement vector. So the point is, this angle here is going to be 90. But the angle here is theta. So that means the angle from the force of gravity all the way to the displacement vector is going to be theta plus 90. And we know that theta is equal to 30 degrees. So that should be 120 degrees. The angle separating the two here is going to be 120 degrees. This therefore enables us to compute the work done by the force of gravity is going to be the magnitude of the force of gravity times the displacement vector in question times cosine of 120. So the force of gravity here is just going to be mg, which is the mass times the gravitational acceleration, and the displacement is going to be 3. So this, the displacement is 0.5. So what this is going to be is, it's going to be 3 kilograms times 0.5 for the displacement times cosine of 120. And you're welcome to calculate the actual number that comes out of this, but I will not get into it just for the sake of time. And then finally, the work done by the force applied. Notice our force applied is this force. This force makes an angle of theta with the displacement vector. You might notice that these two lines are parallel and they are connected by this intersecting line, so we know that these angles are going to be corresponding angles. So the angle here must be theta. So we're going to say the angle here is theta, which means we can calculate the work done by the applied force. The work done by the applied force is going to be the magnitude of the applied force. Oops, that should be A. The magnitude of the applied force times the displacement vector, the magnitude of the displacement vector, times cosine of the angle between the displacement vector and the force applied, because we're looking for work done by the force applied. So then this is going to be 30. The force applied, we were told, has a magnitude of 20 newtons, and the displacement is 0.5, and the angle is 30, so we have cosine of 30. Again, we're going to have some number here. The point is, this is one way, this is what we would obtain if we took this direction of calculating the work done. Suppose we were to try to use this, we were to insist and use this approach. This approach means we have to have all our forces, both the normal force, the applied force, and the gravitational force, we have to have them in unit vector notation. And also the displacement vector must be in unit vector notation. So let's go ahead and take a look at how this works out. I've deleted the question just for the sake of space. I've left what's important. Actually, this is what I'm looking for. This is the picture I'm looking for. In this picture, because remember what we're trying to, the method we're trying to use this time is to find work done by using this definition of the dot product. The one that is vectorial, that depends on vectors being in unit vector notation. Because we have to have our vectors here in unit vector notation, we need to choose a coordinate system. And what I've done is, for simplicity, I've chosen a tilted coordinate system, which is represented by the purple coordinate system. What this means for us is the displacement vector. Remember, the displacement vector is up the incline, and we have designated the incline to be the x direction. What this means for us is the displacement vector in unit vector notation will have 0.5 meters in the I hat direction plus 0 in the j hat direction. That is, the object will not be moving along this direction, it will only be moving up the incline. So this would be our displacement vector. Now what about the normal force? The normal force in this situation will be, in unit vector notation that is, will be given by this. It's going to be the magnitude of the normal force, times cosine of the angle. What is the angle that the normal force makes with the positive x-axis? Well, that angle is 90. So it's going to be cosine of 90, I hat, plus the magnitude of the normal force, times sine of 90. This will be j hat. I hope this makes sense, which means the normal force, the cosine of 90 is going to give us 0. The cosine of 90 is going to give us 0, so this term is going to be 0. This means our normal force will have a 0 I hat plus a magnitude of Fn j hat. The reason why we have 0 I hat is because cosine of 90 is 0. And over here, sine of 90 is equals to 1, which means the component is just going to be the magnitude of Fn, whatever the value of that is. This is just going to be a number, in particular a positive number. So this is what the normal force is going to look like. What about the force of gravity? Well, notice the force of gravity makes a certain angle with the positive x-axis. In particular, the angle it makes is 270 minus theta. So the angle from the positive x-axis measured counterclockwise will be equal to 270, because remember, this is the first quadrant, this is the second quadrant, and this is the third quadrant. So if we begin from the positive x-axis and we sweep all the way to this force, actually this will be equal to 270 minus theta. What is that? That 270 minus theta, that's going to be, 230? Or 240 rather. Right? So this means we can calculate the force of gravity, we can write the force of gravity in unit vector notation. This means Fg will be given by the magnitude of Fg times cosine of, did I say 240? Yes, 240 I hat plus the magnitude of Fg times sine of 240 in the j hat direction. This will all be in newtons. So this will be our gravitational force in unit vector notation. And what about Fa, this force here, this applied force? Notice this force makes an angle relative to the positive x-axis, it makes an angle of 360 minus 30. In other words, if we were to go from the positive x-axis counterclockwise, we would need to sweep a total of 360 minus theta. Remember, the angle here is theta, so this means sweeping over is going to be 360 minus theta, and 360 minus theta, where theta is 30, is going to be 330. So this means the force applied in unit vector notation is going to be the magnitude of the force applied times cosine of 330 I hat plus sine of 330 j hat. That's also in newtons. So now that we have all our forces in unit vector notation, we are ready to calculate the work done by each of the forces. Let's consider the situation where we are interested in work done by the normal force. If we were to calculate the work done by the normal force using the unit vector, the dot product as defined in this situation, we will end up with this. We will end up with the normal force in its unit vector notation dotted or with dot product with the displacement vector in unit vector notation. What this will look like, remember with the dot product, when we take a dot product of two vectors, we multiply the x-coordinate of the first vector to the x-coordinate of the second. And we do the same for the y component. We take the y component of the first, multiply with the y component of the second. And the same with the z components. What is the x component of our normal force? That's 0. So this is going to be 0 multiplying the x component of our displacement vector. But what is the x component of our displacement vector? That's 0.5. So we're going to end up with 0.5. And now we're going to add the products. Remember, when we take the dot product, we no longer have a vector. The outcome is a scalar. So there shouldn't be any I hats or j hats when you have multiplied the two vectors. Okay. So this is the x component of f multiplied by the x component of d. Let's go to the y component. we need to multiply the y component of f with the y component of d. What is the y component of f? Well, it's the magnitude of fn. But what is the y component of d? That's 0. So we're going to end up with the magnitude of fn times 0, which tells us that the work done by friction is going to be, this thing here is going to be 0 plus this thing, which is also 0. That means the work done by the normal force is going to be 0 joules. But notice, this was already, we proved this way earlier. This was true for the normal force when we used this approach. So do you see that these two methods are equivalent? Now, I will entrust to you that you would complete this part, these two sections. That is, for this, use this method to calculate the work done by gravity, and do the same for this situation where you're going to calculate the work done by gravity. In this case, WFG is going to be the x component of displacement vector times this thing here. So what is this going to be? It's going to be 0.5 times the magnitude of Fg. The magnitude of Fg is simply mg, which is 2 times 9.8 times cosine of 240. So what this is simply the half from the displacement vector and the x component of the gravitational force, and that's the x component. What about the y component? The y component is going to be 0 for the displacement, and it's going to be this thing for the gravitational force. But those are just going to give us 0, which means the work done by the force of gravity in this case is going to be 0.5 multiplying 2 times 9.8 times cosine of 240. Now I leave it to you to confirm that what comes out of here is going to be the same as what comes out of here. I think I may have made a mistake. Yep, this here is actually not 2. That's 3. The mass here is 3. This should not be 2. The mass is 3. Let me quickly correct that. That's going to be 3, and that is also going to be 3. And I leave this to you to confirm, convince yourself that the work done by the force of gravity, whether we use this approach or this approach, we're going to get the same thing. And do the same for the force applied. Okay, in order to avoid the video being way too long, I will stop here. And again, any questions, please post them on the comments and I will address them. And for now, I will stop here. See you in the next video.